System design is the process of defining the elements of the system, their interactions, their relationships, and how do they look as a whole. In this video, we will talk about system design and basically we'll discuss everything you need to know to build large-scale distributed systems. This is a roadmap for a system design, so we are not going to take a look at a case study. We'll do that in a different video, but this video will give you all the core fundamental concepts that you need to know about before you design systems. This is part of my roadmap series. So in the first video, the link should be somewhere in above where I talked about how to become a software architect. This is probably at a different level of abstraction where we talk about systems. There we were talking about people and software architecture. So I'm at Roadmap.sh, and just to give a quick guide, you can just go to the website, scan through different roadmaps, developer roadmaps, and when you go to click roadmap, you will reach here, which is system design. I think the previous one that I did is this software architect. Now we are going to talk about system design. So let's take a look and understand what this is, how this looks and about. So we'll start with the introduction. So basically, what is system design? The definition of it, as I was just talking, it's the process of defining the elements, their interactions, relationships, taking a problem statement and doing a complete deep dive into the requirements, the assessment, building a plan, testing the design, ensuring it meets the requirements from a design perspective, testing perspective, and all that. So that's what is system design. Now the way this website flows through is that there's a roadmap and there's a lot of connections to different concepts throughout. I'll also share my experiences across each of them as we progress. Let me just adjust my camera quickly. Yeah, good. So just starting with introduction, what is a system design and how to approach? I think approaching system design is a very fundamental thing to understand before you go deeper into concepts like CAP, load balancing, application layers, and stuff like that. So you should, I'll do a deep dive into this. So you should understand the problem. It implies that take a look at the requirements, gather the needs of the user, understand the constraints, understand the quality attributes, NFRs of the system, and document that overall to understand that this is what you're solving. Know that there isn't a perfect system existing. You will not be able to design a system which never fails. So those kind of requirements, which is 100% uptime and all of that, they are probably the last thing to be discussed. Focused on the core, focus on the user needs, focus on the system interactions, focus on the quality attributes, as I was just saying, like performance, response time, storage, etc. Then understand and identify the scope of the system. Basically, do a boxing around it, define the boundaries, research and analyze existing system. Maybe look at different other systems. Take a look at if there's a competition around. Take a look at if you have parallel systems within your company that has similar architecture and design and all that. Then do a high level design. Outline the main components of the system and how will they interact. It could be about system architecture or a flowchart. Now, one of the very common conversations that arises, how is system design different from architecture? I think they are very similar. There's a lot of overlaps if you think about it. System architecture might be a part of an overall system design, but system design does not get into, as far as I have seen, the intricacies of infrastructure management. How would you design infrastructure? Though it does talk about first principles of how to select the best infrastructure, or what sort of setup you require, but it wouldn't go into making choices such as which vendor to use and stuff like that. So there are differences, but there's a lot of overlap between system design and architecture. And then you refine the design, right? As every design, you should iterate it with your requirements. You wouldn't get it right the first time. Document and monitor, just a standard part of the process. Let's go about it, right? So what is system design? I think we have already talked. Introduction we have already done. So then comes performance versus scalability, right? It's a very good conversation to have. Performance and scalability are usually said in the same sentences, but they are very, very different. So scalable is something that a system can be performant and not scalable. which is to say that a system performs good for a limited number of users but is not able to scale, very much like POCs and all that we build. But a scalable system has to be performant. So that is a thought to ponder upon. So a good description is, if you have a performance problem, your system is slow for a single user. If you have a scalability problem, your system is fast for a single user but slow for a under heavy load. So please make that distinction. Then comes latency versus throughput. I think they are also two important measures of the system. Latency is basically the amount of the turnaround time, the total turnaround time, and throughput is basically the number of requests that are being served. Now, these are fundamental concepts which needs to be known. Availability versus consistency, right? Very, very important concept, CAP theorem. I think consistency, availability, and fault tolerance. Consistency refers to every read receives the most recent write. Availability is every time there is a request to read data without it contains the most recent version. And partition tolerance is the system continues to operate despite some network failures and all that. And basically CAP theorem is a triangle, right? You can have an AP system, you can have a CP system. You will not be able to get a system that is consistent, available, and fault tolerant. So that's what CAP theorem is. And the different databases are designed keeping AP in mind, keeping CP in mind, and all that. Now these are usually more CAP theorem comes into play when you're talking of large scale systems. When you're building simple applications, you might still want to have a conversation around it, but I haven't seen a lot of use cases around this. And then we move on, right? When we have talked about some core principles, we just move on to consistency, right? Consistency is basically the way in which the system behaves. Is it operating the same way as it should under different kinds of load? And that basically defines the different patterns. So you have strong, weak, and eventual consistency. We can look up definitions here. It's an example of weak consistency, eventual consistency. So you have consistency patterns here, and I'm not going to go deep into explaining all the concepts because this is actually very large. I might have to do 2 videos for it, but I'll just try to move forward and see. Then comes availability patterns. So as you can see, these are all principles that there are patterns around. So consistency patterns, then you have availability patterns. And availability patterns are if you're doing replication, if you're doing failovers, there's different kind of patterns like master slave, master, active passive, active. There is I think there's read write and all that too. And then you move forward to understanding background jobs. I think these are very straightforward. You have event driven, schedule driven, and some of them will return data, some of them might not return data. Then on availability systems, I think there's some numbers that you need to be aware of. So there's a 99.9% availability, which is 3 nines. Then there's 4 nines, which is 99.99% availability. There's some systems, but you have to understand that after 4 nines there's a 0, which is 99.90, which implies that the system is not going to be available 0.10% of 0.10% in the year or something, which roughly translates to I think couple of hours, 4 hours or 8 hours or something like that. Like something like an S3 bucket, which is a very durable and highly available setup, they say 99.139, which is more of a theoretical conversation than anything. So I do think they might be able to achieve it in certain scenarios under the recommended architectures, but testing these availability numbers are very, very challenging. Then you go on about understanding DNS. I don't know why they have not covered more information about DNS. They have talked about CDNs, so CDNs are content delivery networks. Basically, when you access an information on the internet, the idea is that you are accessing a most geographically co-located copy of that data. That's what CDNs would do. So CDNs are basically, the world runs on CDN, right? Generally, static files are delivered over CDNs, images, videos, HTML and stuff like that. There has been conversation about dynamic CDNs, but that's very, very nascent. DNS system should have been covered in more. I think DNS is a very important concept. Most of the times you will hear a conversation about single point of failure somewhere when you design systems. DNS actually becomes a single point of failure across the internet in a lot of cases, but the way DNS systems are designed and the different types of DNSs that you have, you should have a good understanding of it. There's top level DNS, there's middle level DNS, there's low level DNS, and then there's different kinds of algorithm by which DNS resolves queries. There's different kind of record that are there in DNS. For example, an NS record is a name server. So you can typically purchase a domain from somebody and tell it that I'm not going to use your name server, I'm going to use the name server for an AWS. So I buy from GoDaddy, but I use Route 53 as my DNS service. You can keep using GoDaddy, no problem there. Then there's mail records, A records, canonical records, and stuff like that. So there's a lot of depth into DNS. If you are understanding system design, I highly recommend you take a look at DNS too. Then load balancers. I think most people think of load balancers as something which is just doing a load distribution to the infrastructure, and they fail to get into the depths of it. You have to understand, and these are very good conversations, like understand the load balancing algorithms. There's dynamic load, most recent cache, round robin, and stuff like that. You could also you should also actually understand, because these days cloud providers offer under a single name a variety of services. So you should understand layer 4 versus layer 7 load balancers, a load balancer versus a reverse proxy, and stuff like that. So that's very important. Then comes application layer. There is just two. I don't think this is a good conversation to have. Service discovery and microservices. I think there's room to have more application layer patterns. There's a whole different architecture, different kind of architectures that could be tapped at an application level, but I think that's okay. This is just the tip of the iceberg. So by now you have understood, looked at it, that the yellow ones that are there, they are the fundamental core concepts. From low application layer, you move on to databases, and databases, boy, have a lot of things. You have different kinds of databases: SQL databases, NoSQL databases, there's in-memory databases, there's graph databases, I even consider sometimes S3 as a database, but that's okay. And then you have these conversations like key value, wide column store, graph databases, replication, sharding, federation, tuning, etc., to be aware about the databases. I'm not going to go into depth in there. From databases, you go to caching. Caching as a core concept is very important, where you cache and different cache strategies. So cache strategies are basically how do you manage and maintain your cache. Is it a refresh ahead cache, write behind, cache aside, and all those I don't think I remember them. At least I have to refer some guides to refresh them, but I can explain these. So caching, where it happens, you can have a client caching. For example, you can choose to store a lot of information in the browser cache, where your client caching is. The CDN caching, obviously, web server, DB, application level, at all forms there's caching available. Then there's asynchronism. I don't know what back pressure is, but basically asynchronism is defining that you have an asynchronous workflows where when you request something, you don't wait for a response or queue in happening. So these are probably setups that can help you achieve asynchronous operations. Then you have idempotent operations. Idempotent operations are multiple without. This is basically the operations. It will have the same effect until over and over again if you do that. I don't know why they have kept it here. I can't guess that. I can understand why asynchronism is connected to communication, but maybe they are describing about the HTTP layers or something like that here, because they are idempotent in nature, I think. So communication, I was right, sorry, here is HTTP and all. So communication, it is very, very important to be aware of different forms of communication. Most people think REST is there, but I think it's important to differentiate between HTTP, TCP, UDP, and it's also important to differentiate at an application level. What are you doing? You are doing REST, RPC, gRPC, GraphQL SOAP used to exist in good old days. And then there are some anti-patterns. Anti-patterns are like opposite of patterns. These are some of the anti-patterns. I have actually not taken a look at it, so I'm gonna skip this and go further down, and then enter into an area which are more which is very very important as for me. After caching, I think monitoring is very important. So you should do health probing, availability monitoring, performances monitoring, and I think modern day users of monitoring has moved over to observability. So instead of monitoring, I will want to call observability here and say that you have the traditional monitoring available, then you have traces that you need to aware about. Logs, traces and matrices is basically what is observability as sum total. So this addresses the part of logs, but how do you build traces into the system, which is addressed by instrumentation. That's important. Visualization and alerts basically implies that how do you see them. Moving from monitoring, I think these are cloud design patterns and different contexts. I'm not going to go deep into it, but because I think this deserves a whole dedicated roadmap to it. But cloud design patterns, there's tons of different patterns on cloud. So when you go on cloud, right, you are typically going to achieve a degree of high availability, resilience and security and stuff like that. So there's different kinds of reliability patterns. These are all reliability patterns, which is availability, high availability, resilience and security. For example, what is geographical? Yeah. So different kinds of patterns from a reliability perspective come into picture in cloud. For example, I'll take storage for instance, right? If you think of a way how cloud works, right, you have one data center which is comprised of one or multiple buildings, and each building has multiple racks inside it. So let's say there's a building A and building B, and we call this as one single data center. There's more correct terminologies I would say, but let's just keep it simple. So test tower A, tower B, made it into one DC. So this is a single DC, and let's say this is in Mumbai. There's another DC which could be present in Chennai, and it will have the same sort of setup. So what we have is we can have tower A, tower B, tower A level replication. We can have tower A, tower B level replication. We can have a DC level replication. We can have a geographical level replication. So there's multiple levels of replications that you can achieve in cloud, and that's basically what geodes is, and this is a high availability pattern. These are some of the ways which you can achieve these benefits or behaviors. And then you can also have a lot of different messaging patterns, tons of different ones like priority queuing, pub sub, etc., schedulers and all that. And then each cloud provider will have a different service which can help you achieve this, or some services are built around these capabilities. There's a very interesting guide that AWS used to publish, which is a well-defined architecture pattern. I highly recommend reading it. That's a very very good place to start and understand how these different patterns are useful. And then you have design and implementation, tons of different one, ambassador, pipes and filters. You can go around, click on each of them, understand each of them in more detail. It will open different documents from different cloud providers like this, and so on and so forth. For example, let's look at CQRS, command and query responsibility, and then it talks about the pattern from it is a storage pattern from cloud design pattern. It's a storage type pattern, and it describes how updates and queries are happening and all that. You can go and read about it. So doing a video with all of these would be too large, so I'm just trying to cut it short. So in short, that's what system design is. That's what system design. I would say that's how you could start learning system design. There's a lot of things outside it. I highly recommend you go through the software design and architecture roadmap, the backend roadmap, and the previous one that I talked about, which is on software architecture. These all of these combined should give you an excellent picture into how to get started into system design, and this could be a multi-year-old journey. All right, that's what I had. I'm gonna stop recording. Thank you. If you have not subscribed to my channel, please do that. Thank you for watching. Bye bye.